This is Lab 2, Motion of a Falling Object for Physics 2211. Here's what we'll be covering in this presentation and video. The purpose of this lab is to observe and determine the effects of gravity and drag force on an object's motion as it falls from rest. This will be done by observing and analyzing the motion of an object that is falling from rest, creating two computational models, one that neglects drag force while the other does not, based on the analysis that predicts the position of the object, comparing the experimental and predicted position data using physics principles. These principles include Newton's second law or the momentum principle. This focuses on the fact that net force acting upon an object is dependent on the object's acceleration and mass. Derived from Newton's second law are two important formulas, the velocity update formula and the position update formula. In this experiment, we'll be observing non-constant velocity due to the acceleration force of gravity, or weight force, which acts in the negative y direction, as well as drag force, which acts in the positive y direction. These two combined will produce the net force. For this experiment, I chose to use a crumpled piece of paper towel as my object, also known as my system. For the surrounding, this includes the forces of gravity and drag. Some important measurements to make note of include the mass of the ball of paper towel and the diameter, which I used later to calibrate tracker and input into the GlowScript code. At the end of this experiment, we'll see that both the observed and predicted models produce similar graphs that implied an acceleration in the negative y direction. However, the graph that modeled the force of gravity as well as drag was much more accurate than the model that only modeled gravity, suggesting the presence of drag force and/or other errors that could have occurred when producing the results. The first part of this experiment includes video analysis and data collection with tracker. Here you can see the video clip that tracks the motion of the falling paper towel. As mentioned earlier, I used the diameter of the paper towel for calibration. The initial position is the origin, which I set at the center of the paper towel ball, as well as the initial velocity, which is 0. The final observed time is also something I will use later for the GlowScript code. Other things to note is the movement of the object, which is in the negative y direction. As you can see in the clip, the paper towel travels a greater distance at each time interval, indicating an increase in velocity, also known as acceleration. Moving on are the computer models and predictions through GlowScript. Here on the left, you can see that I used the initial position, velocity, and time from before. This is used to set the initial conditions for the code. On the right is the calculation while loop, which runs for as long as t is less than 0.6 seconds. I've included the variables f_drag and f of g and their corresponding formulas for the forces present. Beneath is fnet, which is set equal to f of g because we are neglecting drag for this model. Finally, underneath are the velocity and position update formulas that were introduced earlier. For the computational model with drag, the initial conditions stay the same. However, now we have to take the drag constant into consideration. This value was calculated through trial and error until the final position at 0.6 seconds model was the same as that observed. The calculation loop also stays pretty much the same, except for the fact that fnet is now equal to the sum of the force of gravity and drag force. It's difficult to compare the animated models produced, but the differences can be seen with the corresponding position versus time and velocity versus time graphs. While both graphs follow a similar curve for the position versus time graph, you can see that the object travels a greater distance within the time frame when drag is neglected. In the velocity versus time graphs, you can see that without drag, velocity decreases at a constant rate. However, this is not the case for the model with drag. Now, comparing the three models, the dotted line is based on the observed data and the straight lines represent the two computational models. All lines have the same initial position and velocity and account for gravity. The slopes get steeper in the negative y direction, indicating evidence of acceleration. However, as time progresses, you can see that the predicted computational model line without drag begins to deviate from the observed line and the line modeling drag. This deviation is expected. The computational model without drag would assume no force acting opposite of the gravitational force, which is why the object would be predicted to fall faster. On the other hand, the model that takes drag into consideration would have a smaller net force in the negative y direction, clearly better predicting the actual motion of the falling ball. Errors may include human error when tracking, inaccurate calibration, and possibly adding force by hand when dropping the object. To further this discussion, we can address how terminal velocity can be predicted with the models. Since the model without drag does not have the force of drag to counter the force of gravity, it would not be able to predict terminal velocity. However, the model with drag could. This would occur when the force of drag pointing up has exactly balanced the force of gravity pointing down. This also means that net force would equal 0. If the object was initially thrown downward, the terminal velocity would still stay the same, since it is dependent solely on the drag force that balances out the force of gravity, not initial velocity. Based on the computer model of the object's velocity as a function of time, the velocity begins to flatten at around 3 to 3.5 meters per second at 0.4 seconds. If the object was thrown downward, it may reach terminal velocity at a different time, but it would reach it nonetheless.